All right, guys, so we had just left off comparing these two functions graphically. And so the last thing that we want to do is to confirm that when we do the function composition, so we can call that f of g of x, or if you want to write it like this, f of the inverse of f at x, that result needs to be x, and then we reverse it, it also needs to be x. So let's go ahead and write out our two functions. We have f of x equals x cubed, that was our original function. And then we have our inverse was the cubic root of x. So if we take the function and evaluate it at its inverse, of x, what that means is we're going to take the cubic root of x and substitute it in for this x here in our original function. So it'll end up being cubed. Now if you take the cubic expression of a cubic root, you're just going to be left with what's inside, which is x. And if we were to flip-flop that operation, if we take the inverse and evaluate that at our function, what that means is we're going to take x cubed, but then take the cubic root of that. And so then these exponents would divide, and we'd also be left with x there. So it checks out. Either way, we're good to go. We found the right inverse. Example number 4 is just another practice for finding the inverse of a function. So this one says, find the inverse of the function for what's given below, and we have f of x equals 2x to the 5th minus 7, which is the same thing as saying y is equal to 2x to the 5th minus 7. So we're going to swap x and y to find the inverse. So that's going to give me x is equal to 2y to the 5th minus 7. So we need to start getting y by itself. So I can add over 7. X plus 7 equals 2y to the 5th, and then I can divide by 2. Running out of room a little bit here, so I've got x plus 7 over 2 equals y to the 5th. So the last thing I need to do to get y by itself is to take the 5th root of both sides. And so I'll have y is equal to the 5th root of x plus 7 over 2. And I can either call it y or I can call it the inverse of x. And so that's going to be my final answer there for my inverse function. And I could use the previous methods that we've checked out to identify and confirm that it is in fact the correct inverse, either using function composition like what we just did up above, or by graphing, or by picking an input and output relationship set and seeing that when I plug one into one and get out a value, and then plug that value into the other one, that it matches up correctly. Last thing we're going to cover today is the idea behind what's called a true inverse. So in order for something to be a true inverse, what we've talked about is that the x and y values need to be flipped. So if the x and y values are flipped, what that really means is that the domain and range are flipped too. But there's a little bit of a problem there because some functions have limited domains and ranges. And so not all functions are going to have what we call a true inverse value. And one such function like that is going to be this one here, f of x is equal to y squared. So let's talk about this function. If I have f of x is equal to y squared, is equal to x squared, I can also write that as y is equal to x squared. So if I want to start finding the inverse, I'm going to swap x and y. And if I do that, I'll have x is equal to y squared. But then if I try to get y by itself, I would take the square root of both sides. The issue here, though, is when I take the square root of x, I technically have both the positive square root of x and the negative square root of x, two different functions. So what that means is our even valued powers, so like x squared and x to the 4th, those kinds of functions aren't going to have a true inverse. They will have an inverse over a specific set of x values. So we'll get into talking about graphs a whole lot more tomorrow. But if you just picture the general graph of x squared, it's a basic parabola. So let me sketch out a parabola here. So this parabola, and I'll put it in pink here, x squared looks like this. So if you imagine just positive square root of x, if I just take this piece here and I graphed it, And you can graph this on your calculator, or if you pick some points and plot them by hand, you can certainly check them out that way too. But that graph is going to look something like this here. And so it is going to meet what it means to be an inverse, but only for positive x values, because this function will never be negative. So we have a test for whether or not something has a true inverse, and we call it the horizontal line test. So it's kind of the opposite of the vertical line test that we've done before. So vertical line tests tell you if something's a function. Horizontal line test tells you if a function has an inverse. So if we consider our original x squared function, if I draw a line through it, it hits my function twice, here and here. So what that means is that that function will not have a true inverse. It's only going to have an inverse that works over a specific set of values. So for instance, x greater than or equal to 0 would work here. So we'll talk about that, and we'll talk about our graphs more tomorrow. That will be our focus, is going to be on how we graph square roots and cubic roots and how we can move those kinds of graphs around as well. But our key focus here is that we can always follow the process of flipping our x and y variables to solve for the inverse function, but that we do just need to be aware with the horizontal line test that some of those inverses will only apply over a specific domain. So that's it for your video. Go ahead and get started on the assigned problems from section 6.4 tonight, which begin on page 442. Thank you, guys.